let's begin by considering this simple first problem. We have a cylinder upside down here with a piston inside it. Trapped in the middle space here is air, and we also have a small valve right here that has to be opened in order for us to allow for gases to go in and out of this cylinder. So what we want to do is find the force that we have to apply through this little lifter rod in order to get this valve to open. And then also, if we know the temperature of the air inside this cylinder, what would be the specific volume? So let's go ahead and begin by drawing the cylinder. Here it is, and we have a little lifter right here that we're interested in. And of course, on the other side of this, we have the piston head, which in this problem is not moving. We have air, that's gas, inside. And we're considering the case that the pressure in here is 700 kPa, and that the pressure out here is about 100 kPa. We also know that the temperature here is 200 degrees centigrade. We want to find the force that we have to apply to this lifter, and we want to find the specific volume of the air inside. So our governing equations are going to begin with really how does pressure and force relate. So a pressure is a magnitude of force over an area. So in order for us to try and figure out what kind of force we need to relate pressures and areas, and at the same time we want to consider the sum of the forces acting on our small little lifter here. So the sum of the forces equals the time rate of change of momentum. And we want to consider the special case that this is balanced. So once we find the force that's required to balance this situation, if the lifter were to apply any more force down, we would open up and allow the air gas out. So we're going to find the kind of the limiting case where we're balanced, and then say for any force greater than that, the lifter would open. So we have a situation where we need to draw a free body diagram. Here's our little lifter again. We're going to have the atmospheric force pressing down. We're going to also have some force applied through this lifter rod. And lastly, we have the force due to our air blob inside. So adding up these forces, we are looking for the balance stationary point. We need to write down a constitutive equation for all the forces that we do know. So P naught times A, and if we choose this to be our j hat direction, this is going to be in the minus j hat direction. The atmospheric force presses down, whereas the blob force, the force of our simple compressible system inside here, goes up with a pressure P. And so we are looking for the force applied, of course. So the force applied is equal to minus Fp naught minus Fb. So this is going to be P naught A in the j hat direction minus P A in the j hat direction. So we are going to have P naught minus P times A in the j hat direction. And that's our force. Let's see what MATLAB has to say about this. It's a very simple computation. So we start off with a very simple initialization of the MATLAB, clear, close all CLC. Let's enter in our specifics for this first question. So the pressure is 700 kPa. The temperature is 200 plus 273.15. The atmospheric pressure is 100 kPa. And the area in this case is going to be 10 centimeters squared, and we forgot to label that. It's given to us in the problem statement. A is 10 times 10 to the minus 4th meters squared, 10e to the minus 4, and we're going to go ahead and find the force applied then for balance would be P naught minus P times A in the j hat direction. Let's run this little code, and this comes out to be minus 0.6, and we know this is going to be in kilonewtons. How do we know that? Because this pressure here is in kilopascals and this area is in meters squared. So what comes out of there is kilonewtons. So for any force down greater than 0.6 kilonewtons, the lifter opens. So that's our first answer. We're really looking for any force bigger than this in magnitude. So really we're looking for something technically that's less than this since it's negative. Okay. The next thing we want to do is we're given an air-gas blob here, and we know the pressure and the temperature. Let's go ahead and find V. So we're going to need an equation of state. For air that's gas, it would make sense for us to use the ideal gas law. Here this is R for air, which if we look it up is 0.287 kilojoules per kilogram per Kelvin. That's in table A1 of our appendices. And we can go ahead and compute V now, RT on P. And what's that going to be? So plugging in our value for R here, 0.287, we're going to have V equals R times T on P. And we run it, and we know that this number is going to be in meters cubed per kilogram, based upon our work with the ideal gas law up to this point and these standard units that we're using. So that's the first problem. Let's take a look now at the second problem on the exam. So the second problem consists of 4 equation of state problems. Let's take a look. Each one of these is for water. So our first guy here has H2O, and we're given a pressure of 300 kPa, and we're given a quality of 0.5. So instantly, because we're given the quality, we know that it's mixed. So our EOS is for H2O that is mixed, and we know that's going to be table A4-5, right? We have boiling going on here since part of it's gas and part of it's liquid. So our temperature is a simple lookup. We go to our table or here and we look for our saturated tables, and we find, hey, here we go. Our pressure in table A5 is 300 kPa, and our temperature is given here as 133.52 degrees centigrade. That's done. And our specific volume would be VF plus X times VFG, since we're mixed. Let's grab some values. So this is VF, copy, and we'll go down here and clear this so we can start new and fresh. VF is that. VG will be its next door neighbor at 300 kPa. VFG is just VG minus VF, and V is equal to VF plus X times VFG, and of course we better tell it what X is. X was 0.5. And we run this, and we get our volume here is 0.3034 meters cubed per kilogram. And that problem is done. Now we're on to the next one. Once again, we know we have H2O. And reading the problem statement, we now have a temperature of 80 degrees centigrade and a pressure of 5,500 kPa. So our first step here will be to find the phase. We're going to draw what we have, which is P and T. So let's go ahead and find at a temperature of 80 degrees what would be my boiling pressure. I'm going to our tables here. Oops, that's not what I wanted. Going to our tables here. At 80 degrees, our pressure should be 47 kilopascals if we were boiling. Of course, our pressure is way up here at 5,500, so we are liquid. Okay, so what we'd like to use for liquid H2O is table A7. So let's go to table A7. Table A7, and we look in here and we have this is 5,000 kilopascals, and this is 10,000 kilopascals. We want somewhere in between at 80 degrees centigrade, so we're going to have to do table creation. 5 megapascals, and we want 5.5, and we have 10 in the table. Our temperature is in the table, thank goodness, of 80 degrees centigrade, so we're going to have 0.00102, and at 10 we would have, this is going to be 7.00102.4. So let's do a quick interpolation to get this beautiful number here that we're looking for. And so we copy this and let's stick it into MATLAB. We have V at 5 is going to be that number, and we have V at 10 going to be his next door neighbor. We've already copied down into our table creation process. Then we find our volume that we want. It is a simple interpolation between 5 and 10, V5 and V10, and then we have our 5.5, and running this we get that our volume is in between, and we probably could have guessed this since it's so close, 0.001.026 meters cubed per kilogram. And so we are done with the second problem. Now let's go on to the third problem. The third problem has a water blob. We have a pressure of 1,700 kPa, and we have a volume of 0.16 meters cubed per kilogram. So we're going to find the phase first, as we do, drawing what we have, P and V. The PV picture is a vapor dome. Of course, it's our critical point. So at a pressure of 1,700, let's go look up some volumes. Our volume at 1,700. So we aren't quite in the table, are we? We're at 1,750 and 1,500. So if we look over here, our volume of fluid is very much smaller than our given volume of 0.16. And our volume of gas is still smaller than 0.16. So that means that we are definitely over here. All right, since our VG is at maximum 0.11 max. Right, and it's not 0.11. In any case, ours is 0.16. So we are a gas. We know for H2O that's gas, our table A6 is our equation of state. So let's go take a look at our table A6. Table A6, we scroll down to our given pressure of 1,700, so 1.7. It's not in the table, but 1.6 and 1.5 are. And reading across here, since we're looking for a temperature, reading across the table here, we have, let's see here, 0.15 here, 0.12, it's too small, 0.17 here, and 0.156. So our value seems to be in between those two. This is definitely bigger, and this number is definitely smaller. So let's go ahead and interpolate at 350 and see what we've got. So we're going to go ahead and do this in MATLAB briefly. So let's interpolate. Do it up here. So V at 1.6 is, or better yet, V at 350 so V at 350 degrees is going to be an interpolation between 1.5 and 1.7. Excuse me, between 1.6 and 1.8. Of this value at 1.6 and this value at 1.8 and 1.7. So this number that we just found, V350, is actually bigger than our value. So we need something smaller to, let's go ahead and draw the table now. It'll make more sense. So we have 1.6 megapascals, 1.7 that's not in the table, 1.8 that is. We just found for a temperature of 350 that our value at 1.7 here would be 0.1646, and our value that we're interested in is 1.600. Let's go over and take a look. For us to get something now that's smaller, we would have to go up. So we're going to be interested in 300 now, and grabbing a value at 300. Our value, of course, that we're interested in is 1.6. So at 300, let's calculate V at 300. And all of this is going to be copied until we get to right here when we grab our 300 values. Oops. And so V at 300 now we've just found is 0.1495, and lastly we interpolate to get our desired temperature, which is what we don't know in this problem. Let's grab it. So T is going to be an interpolation between V300 and V350, values of 300 and 350. And lastly, our value that we're interested in is 0.16. And running this, we're going to get $335 or 334.8. 334.8 degrees centigrade. And we're done with this problem, and let's finish off this very briefly. So we have one more blob problem to do. Let's see if we can fit it on this page. We have H2O, and we're told that it has a temperature of 90 degrees C and a pressure of 100 kPa. Once again, we need to find the phase. So let's draw the vapor pressure curve, P and T. So if I look up at a temperature of 90 degrees centigrade in my vapor pressure curve, 90 tells me the pressure would be 70 for boiling. Of course, my pressure is 100, so I'm liquid. So I'd like to use H2O that's liquid tables, which is table A7. But I can't because table A7 doesn't have enough data. So instead we assume it's incompressible. So that means we're going to use V is equal to VF at my given T, which in this case is just 0.001036 meters cubed per kilogram. And we are done with this problem. So now let's go on to our last problem on the test. So this last problem, let's quickly consider it. We have a piston cylinder arrangement, like we're familiar with, that's constrained by a spring. And we have some interesting information given to us in this problem about the spring. We have atmospheric pressure out here, and this spring is such that dP, specific volume, d little v, is equal to km on a squared, we'll see that in a second, is a constant given to us, 8 times 10 to the 4th kPa meter cubed per kilogram. We know that there is H2O inside this guy, and of course the mass is constant. We're told that the initial pressure in here, P1, is 5,000 kPa. T1 is 400 degrees centigrade. And we're also told the initial volume is 0.1 meter cubed. So that's a lot of information. The system cools reversibly, supposedly due to, say, an ELF that's slowly bleeding heat from the system, to a state 2, where this new pressure after the heat transfer is 1,200 kPa. In this problem, we're asked to find the mass of the air blob. We're asked to find T2 and V2 at the second state, and we're supposed to sketch the process. Those are all the things we need. So we need to come up also with some governing equations to help us out. Probably you've noticed that we have two independent intensive thermodynamic properties at state 1 from which we can get the specific volume at 1. Knowing the specific volume at 1 and the total volume at 1, we can get the mass, right? Because we know that mass is basically equal to the volume over the specific volume. To use this, we need an equation of state, which means we need to know the substance, which is given, but we have to find the phase, either at state 1 or state 2. And then lastly, we're probably going to use the sum of the forces external to the system equals the time rate of change of the momentum. In this case, this is 0. We're assuming a reversible process being driven by an ELF. So to use Newton's second law, of course, we need to draw a free body diagram. Here is our diagram. We're going to have the spring force. We're going to have the force of the atmosphere. We'll have the force of gravity. And lastly, we'll have the force of our simple compressible system, our blob inside the cylinder. we know we're going to sum these forces. And so Fp naught plus Fs plus Fb plus Fg all equals 0, where we know the constitutive equations. Fp naught is simply p naught times a in the minus j hat direction, if indeed I choose j hat to be up. F of my system is p times a in the plus j hat direction. I have the force of gravity, which is the mass of the piston times gravity in the minus j hat direction. And lastly, I have the force of the spring, which is going to be equal to k times y in the minus j hat direction. And here the problem becomes a little bit more tricky than what we've seen in class, because we're not told at what state our spring is relaxed, right? So say this arbitrary state right here is the state at which the spring is relaxed. That might help us out to just kind of assume an arbitrary state and see what the rest of this problem will allow for us to unfold. So we have all of these constitutive equations, and let's go ahead and plug them in. When we do, we're going to find that in the j hat direction, we get a pretty simple expression. P equals P naught plus mass of the piston gravity over area plus K on A times Y. Of course, we would like to rewrite this in terms of the geometry of the situation, right? So we're going to have this y equals 0 location right here. So we might call this V naught here. And then we're going to add on to that some amount of volume, y times A, to give us our total volume. In other words, our geometry equation here is such that the volume would be equal to this initial volume plus AY, or y is going to be equal to V minus V naught over A. We could also factor out a mass from both of these. Y equals m over A times V minus little v, minus little v naught. So this is now written in terms of specific volume. Let's go ahead and plug that in, and we would get that the pressure now, as a function of the specific volume, would be P naught plus the mass of the piston gravity over the area plus K on A squared m times V minus V naught. So we still are in trouble here. We got this V naught expression that we're not really familiar with too well. Let's we do see a Km on A squared here that seems to be reminiscent of what we're told about in the problem statement. Let's see what's going to happen, however, if we just apply this at state 1. So the pressure at 1, that's going to be P at specific volume 1. It's going to be P plus mass of the piston gravity over area plus Km on A squared times V1 minus V naught. Now let's try something interesting. So this is at state 1. Let's subtract these two expressions. We get P minus P1 equals, well, P naught minus P naught, that goes away. These two guys would go away. And we would get Km on A squared times V minus V naught minus a Km on A squared times V1 minus V naught. And what we're going to see here is, interestingly, this minus V naught times Km on A squared is going to add to a plus V naught Km on A squared to get rid of this term. And that leaves me with a very simple expression for the pressure now. Pressure is going to be P1 plus Km on A squared times a V minus V1. This is pressure as a function of volume, where I've replaced all of these crazy constants that appear right here in terms of P1 and V1. So I've gotten rid of P naught, mass of the piston gravity area, and this initial rest volume. That's pretty nice. So this is our first kind of nice expression that we've come to that's new, and it basically came from taking this general term and subtracting the pressure at state 1, right, I subtracted those two to get this term, which simplified to this new pressure expression. Let's go ahead and differentiate dP dV. Well, the derivative of P1 plus Km on A squared times V minus V1, derivative of P1, that's 0. Km on A squared times V1, that's a constant, that's 0. So I'm left with just this linear term here, Km on A squared, and it's a number that I know. 8 times 10 to the minus 4th kilopascals meters cubed per kilogram. Great. So that means that in this expression here, I know this grouping. I know specific volume 1, which I can find, and I know P1. So lastly, I can find P2. So at 2, P2 is going to be P at V2, which will be P1 plus Km on A squared times V2 minus V1.